Shall we get started? Students who are online, are you able to hear me?
Yes, sir.
Good. Okay, so we'll get started. Right. So we have completed the first chapter, that is electric charges and fields. So what is the objective of that chapter? Let's recollect so that you'll understand why we are studying this chapter. So what is the objective of electric charges and fields? So we discussed about the charges and system of charges and the amount of electric field intensity those charges were able to create. So how did we calculate those values? So if the system were made up of point charges, we used Coulomb's law. If the systems were not made of point charges, we used Gauss law. So Gauss law was used for symmetry and all those things, right? There are 3 derivations and 3 applications which we had for finding the electric field due to different kinds of extended charges, right? So with that, our concept or I can say the context of finding fields due to system of charges is over, right? If you see the name of this chapter, it says it is electrostatic potential and capacitance. So electrostatic potential, if you see, it is actually an extension of the previous chapter. Because electrostatic again, right? It refers to the charges at rest. Then what is this potential all about? Secondly, you have a concept called as capacitance. So capacitance is basically like the property of a device called as capacitor. Property of a device named capacitor. Like how you have resistance, the property of a device named resistor, you have capacitance as the property of a device called capacitor. Right? So shall we get started? Yes. So first write down the heading as electrostatic potential. Okay, that is the first part of the chapter. Proceed. in our day-to-day life, where do we come across this word called as potential? What devices use this name? This concept we have already learned in your 10th grade. That is gravitational potential. What is potential difference you are trying to talk about? It is measured for which device? Voltmeter. It is measured by the device. Potential difference is measured by voltmeter. That's a different story. I'm asking potential difference is a parameter which exists for which device is whatever. You talk about batteries, right? You talk about cells. So all these have a positive and a negative terminal associated with them. And due to the positive and the negative terminal, what can you say? Due to the positive and the negative terminal, there I can say that there is some potential difference existing. That is what we say in layman point of view. But we need to understand what exactly that means in terms of science, right? So even before, as the name of the chapter is electrostatic potential only, but before I explain what is electrostatic potential, I need to explain you what is electrostatic potential energy. Okay, that is the first concept. So electrostatic potential energy is represented by the symbol U. Okay. Now, so I'll tell you how we are supposed to analyze a particular physical quantity which is given. Okay. Energy refers to what? What does energy mean? Energy is the capacity to do work. So whatever work you do on a system or whatever work is done by a system will always get stored in some form of energy. Here, potential refers to what? Virtue of rest or position. Or I can say virtue of rest, position, or configuration. Virtue of rest, position, or configuration. Right. So what does this electrostatic mean? Charges at rest. Now our job is to connect all these dots to get the meaning of what is electrostatic potential energy. Okay. For that, we need to recollect the concept of source and test charge. Listen to this. If at all I have a source charge, what do I have? I have a source charge, and around the source charge, what is present? So there is electric field present. So any point outside this electric field is called as. So any point outside this electric field is called as infinity. Accepted? Right. Now see, the source charge capital Q and the test charge Q naught, are they going to interact with each other? This is okay or this is okay? This is better. Okay. So are these two charges going to interact with each other? No, right? So if we need to make them interact, what am I supposed to do? I'll bring the test charge into. So inside the electric field of the source charge. Okay. By doing so, there is a possibility of one thing to happen. What is it? The test charge will start experiencing a force due to the source charge, and the vice versa will also happen. In the sense, the test charge will also exert a force on the source charge. But if you want to eliminate the second process, then what you're supposed to do is you need to have the magnitude of test charge as small as possible so that when it enters the field, the force that it tries to exert on the source charge is very less. Means the test charge should have magnitude of that small value. That is one point to be noted. Secondly, the test charge you're trying to move into the electric field should be moved as slow as possible. Why am I saying as slow as possible? Because what are we trying to calculate here? Electrostatic what energy? Potential. So potential is related to the rest or system or configuration. The position or configuration means it depends on the position of where that particular test charge is there. If at all the object had some velocity, apart from potential energy, you can also define kinetic energy. We are not interested in kinetic energy. We are only interested in potential energy. That is the reason why it should be ensured that the charged particle is moving as slow as possible. Wash your face. Right? Now, when the charge is moved from infinity to a point within the field, let's say to a distance r, and how is it moved? It is moved as slow as possible. Never forget this. Okay, when this is going to happen, now can I say that there is going to be a force that is going to exist between them? So what is the value of force when, wait, when the test charge is moved from infinity to a point at a distance r from source charge. Okay, what will happen? You tell me. There is force experienced by it, accepted, of what magnitude? There is a force experienced by it of magnitude F is equal to K capital Q into Q naught divided by the distance square. Accepted. Is that right? Now, see, you need to think of one point. So I told you I'm going to connect all the dots. Now I'm going to give you the definition of what is electrostatic potential energy. So what energy is capacity to do work. Right? Potential is with respect to position, electrostatic is with respect to charges. So connecting all these dots, it is like this. The amount of work done. Listen to this first, then you can write it. The amount of work done. Okay. Whenever you are defining work done, it is always important to mention work done by which force. Okay, here there are two forces existing. One is the force due to the system itself, that is electrostatic force, or the second is external force. Out of these two, which one am I trying to talk about? That's where we go wrong. It is actually work done by the external force. So I reiterate, the amount of work done by the external force to do what? To bring a test charge from infinity to some point within the electrostatic field of the source charge. Right? When you're going to do this, you're doing some work, and that work is what is going to get stored as electrostatic potential energy, and that is what we are going to calculate mathematically. Right? We are still sticking to the basic, nothing outside. Now I'm going to ask another question. What is work done? What is the mathematical expression for work done? Force into displacement into cos theta. That is Fs cos theta. Is there any other expression for work done? See, work done is equal to F vector dot S vector is one way of writing, or Fs cos theta is another way of writing, right? Or else there is something called as integral of F vector dot dr vector. Have you seen this? Now comes an important question. When do I use F vector dot S vector? When do I use integral of it? You need to answer that question. No, it is not with respect to distance. There is something else. It has nothing to do with the distance. It has something to do with some other parameter. It's the basic thing that we need to know first. The first question you need to ask is, work is done by which force, and whether that force is a constant force or a variable force. So what do I mean by constant force? F vector is equal to 5 I cap. Is it a constant force or a variable force? It is a constant force. Whereas, can you define how a variable force looks like? Guys, these are all the basics you need to know. So F vector is equal to 5x I cap. Is this a constant or a variable? Why do you say it's a variable? Because force is a function of displacement. So if force is a function of displacement, it is variable force. When it is variable force, you need to use this formula. When it is constant force, you need to use the first formula. Is this clarity there in your mind? Right. Next time you can answer it, right? Good. No. K capital Q into Q naught divided by R square. Please tell.
When it is not into the electric field, then it is the what kind of electrostatic?
That is right. I'll tell you how it actually happens. Okay, you have written this expression, no? So I forgot to give you the definition in the first place. Please write down the definition. So if you have space in the top, below electrostatic potential energy, please write down the definition. The amount of work done by an external force, to move the test charge, from where? From infinity to some point within the electrostatic field of the source charge. Very good. So I reiterate, I repeated, listen. The amount of work done by whom? By an external force to bring a test charge from infinity to a point within the electrostatic field of the source charge. Are you able to visualize what I'm trying to say? Yes. Now, what are we trying to do? We are trying to derive a mathematical expression for it. Now, I have already mentioned about work done. And the definition also says...
Can you repeat after infinity?
Yeah. So, listen to this. The amount of work done to move a test charge from infinity to a point within the electrostatic field of the source charge. Within the electrostatic field of the source charge. Is that clear? Yes. So now you guys think and tell me what force does this expression represent? This is actually the electrostatic force, right? But what does the definition tell us? It is the external force. So logically, let's think of one factor. If this is the direction of electrostatic force, are you accepting this? Why did I take it as right hand side? Because source charge, which I consider is positive, test charge by default is positive, so it repels. Now, what direction should I apply the external force? I need to apply the external force exactly in the direction opposite to the electrostatic force, right? But I have to strictly stick to the definition. So if I have to do that, I'm going to mention something important. Listen, electrostatic force is going to be approximately equal to the external force, right? I'm saying it is approximately, it is not exactly equal, because which one is moving the, logically think guys, when I bring the test charge and keep it at point P, okay, when I keep it at point P, if at all your hand is not there, okay, if at all your hand is not there at point P, what would have happened to the test charge? It would have jumped away. But to balance it, what are you supposed to do? You need to apply an external force in the opposite direction. You're doing it. But at the same time, you need to achieve something. What are you doing? You're still moving it. But you're moving it as slow as possible. When you're doing it, you need to create an unbalanced force. So when there needs to be an unbalanced force, which force is supposed to be greater? The external force should be able to overcome the electrostatic force, but the extent to which the external force is overcoming the electrostatic force is very, very, very small. That is what I meant by approximately equal. Is that clear? This is a very, very important point to be noted. Tomorrow when you're reading, right, you will get a doubt that external force and electrostatic force, if they are same, how is even the charge moving? It cannot move, right? So what are we trying to do? This external force, let's say it is causing a displacement by a small distance dr. Towards where? Towards the source charge. When you do this, then can I write the small amount of work done by the external force is equal to F vector dot dr vector. So what is F vector? K q into q naught divided by r square into dr. Accepted. Is there any doubt in this? Right. K q q naught by r square into dr. If you want, I can write cos 0. Because external force and dr both are acting in the same direction. Right. Now, cos 0 is going to be 1. I need to calculate the net work done by the external force. When that is the scenario, then I need to integrate on both the sides. It is kq into q naught divided by r square into dr. Now tell me the limits. Limits will be given by the definition itself. Read it. Where are you moving it from? From infinity to some point r. Right? So this is equal to what can be taken out of the integral? What are all constants? Case q, q naught. All these are constants. So k, q, q naught, if it is a constant, integral of dr divided by r square from infinity to r is equal to k, q into q naught into what is integral of 1 by r square? So integral of x power n dx is equal to x power n plus 1 by n plus 1. Correct? Upper integral of x power minus 2 dx will be equal to how much? X power minus 1 divided by minus 1. That is minus 1 by x actually. See, if at all you recollect from differentiation, derivative of 1 by x is minus 1 by x square. So integral will be reversed. So it is minus 1 divided by r from infinity to r. What is going to be the answer? Minus k q into q naught divided by r plus k q into q naught divided by infinity, and this value comes out to be 0. Is everyone comfortable with definite integrals? Upper limit minus lower limit, right? So answer will be minus k into q naught divided by. And what did we actually calculate? We calculated the work done by whom? External force. And this is what is the electrostatic potential energy, which is represented by the symbol capital U. Does it make sense? Right? So please write it. Minus is a very, very important. From where? There is enough.
Sir, could you explain why you are integrating the work done?
Because you calculated small amount of work done. No? When the displacement is very small, dr, then the work done is also small. So if you want to calculate the total work done, then you always need to go with integration.
Okay, sir. Okay, sir.
Got it?
Sir,
Yeah, tell me.
sir, when you mean the electrostatic force is almost equal to the external force, you mean that when we are moving the test charge slowly, it has to overcome it, but it's not exactly equal to that electrostatic force.
It is not exactly equal. The external force is slightly greater than the electrostatic force. Let's say the electrostatic force is 3 units. The external force will be 3.000001 units. It will be that small. The limit value is so small.
Okay, sir.
Okay. Got it, guys? So when you look at this formula, right? This is the actual formula. You need to, whenever you're using this potential energy formula, you always need to have that minus. Okay. Now, what does this minus sign indicate here is the negative sign indicates that electrostatic force is conservative in nature. You know what is conservative? You know what is with the meaning of conservative force? Conservative force has force itself has direction, whether it is conservative or non-conservative. Final bar. See, to be more specific, right? If you take a round trip, so work done by a conservative force in a round trip is always zero. whereas the work done by non-conservative force in a round trip is non-zero. Examples of conservative force: gravitational force, electrostatic force is a conservative force, whereas non-conservative forces are the ones which are repulsive in nature, which are resistive forces in nature. I can say friction, air drag, viscosity, all these things are non-conservative forces. Is that clear? Am I clear, guys? So if you observe, this expression is something similar to what we saw in the previous chapter. What is it? Electric field. See, look at the numerator. Two charges are there. Denominator is dependent on distance. So this is almost closer to some other expression that we already saw. It is something similar to Coulomb's law, right? The force existing between 2 point charges, except the fact that you have r square there in the denominator. Here you have r. So whenever you want to calculate electrostatic potential energy, how many charges are needed? The minimum number of charges that are required are 2. You should always have this in your mind. So they will always ask the question like this: calculate the electrostatic potential energy of the system. Okay, then you need to have more than 2 charges. But what is the name of the chapter? Electrostatic potential. It is not potential energy. Now we need to see what is electrostatic potential. But before that, can you tell me these following things? Is it a scalar or a vector quantity? Electrostatic potential energy, is it a scalar or a vector quantity? It is a, don't guess, confident it is. Is it a scalar quantity? Why? That minus sign, is that what you're trying to say? Think about it. What is the definition starting with? Work done is what? It's scalar. Energy is a scalar quantity, right? So it is a scalar quantity. Then what about the units of it? If I talk about the unit, that is, when I say unit, it is a SI unit. It is going to be in terms of joule. Work done is in joule. That's it. Right. Now see. The next point that we need to understand is electrostatic potential. This is where I want your concentration, because the definitions are very much close. So this electrostatic potential is the one I told you about battery. Let's say you're going to a shop. You know these AA and AAA batteries, right? You go and ask for a AA or a AAA battery. Okay, let's take AA as of now. When you buy it, have you ever seen the potential difference on top of it? Have you ever seen what is written on top of it? How many volts it can supply? Have you ever observed it? Or you just take a AA battery, Duracell, and come off? That's what you do, right? Next time, observe it. Okay, whenever you are putting it for a remote, you will generally use a AAA battery because it will be thin like a pencil. And for other devices, so some remotes demand a AA battery also. So next time you observe the value that is written on top of it. Actually, 1.5 volt into 1.5 volt battery, 9 volt battery, which will be fat. Right, you will connect a rubber kind of thing on top of it. Have you ever observed all these things? You would have at least seen, right? Next time, observe all these things. That's generally a 9 volt battery. You're using the word volt, right? What does it mean? What does a battery have in the first place? So it's a chemical expression. That's a different story. It has a positive terminal and a negative. Positive and negative are related to charges. So there is a potential with respect to 1 point positive charge, potential with respect to negative charge. So the difference between these two potentials is what we call it as potential difference, right? So if I have to be more specific, right, when you go to a shop and buy that battery and come, it is actually not called as potential difference. It is called as EMF. It's called electromotive force. What is it? We will see it in the next chapter. Let's not worry about it as of now. As of now, we will think it as potential difference itself because we don't have knowledge of EMF, right? Are you guys in agreement? So it is potential difference as of now. Means what? Positive terminal has the potential. Listen to my statement carefully. Positive terminal has a potential. Negative terminal has a potential. Means there is a specific value associated with it. In the sense, I can ask you a question. You told me 1.5 volt, right? Generally, you know how a cell looks like. Cell is basically a positive and a negative terminal. This is from your 10th grade knowledge, right? Let's say this has a potential. The positive terminal has a potential of 2.5 volt. Then what should be the potential of negative terminal for it to generate 1.5 volt? It should be minus 1 volt. You're able to understand what I'm trying to say. So 2.5 volt is a specific quantity related to, sorry, it should be 1 volt. Okay. So 2.5 volt is specific with respect to the positive charge. 1 volt is with respect to the negative terminal, not positive charge, positive terminal. And 1 volt is with respect to negative terminal. So that the potential difference between both is 1.5 volt. Similar. So you're able to understand this point, right? I'll come to that. Now, what am I trying to define? Am I trying to define electrostatic potential or potential difference? I'm clear about it, right? It is potential. So when I talk about electrostatic potential, this is also work done only. By whom? Listen to this, then you can write it. It is also work done only. But by whom? By an external charge. So what is the definition I gave you in the previous case? For electrostatic potential energy, what did I say? Amount of work done by an external charge to move a test charge from infinity to a point in the electrostatic field, right? This definition is also almost closer. Listen, work done by an external force to bring a unit, or I'll change it like this: amount of work done per unit charge to move it from where? The same infinity to a point in the electrostatic field. Isn't it confusing? Right? How many of you are confused? Read the definition. I want you to figure it out. What is the difference between both? There, you are moving a test charge from infinity to this point in the electrostatic field. Here also, I'm defining it in a similar way. But what is the statement I used? Amount of work done by external force per unit test charge. So, what is the meaning of it? So, I need to divide the potential energy, because work done is always stored as potential energy, and divide that potential energy with a unit positive test charge. That particular quantity is what is called as electrostatic potential. I'll give you a simple example. If at all you are asked to define speed, what would you say? You say distance traveled by time taken. More mature way of defining this: distance traveled per unit time. So whenever you see that word per in physics, after the word per, whatever is coming should be in the denominator. So you generally say unit time. Unit doesn't mean 1 always. Time can take 2 seconds, not like every object is going to cover the distance in 1 second. No. So that unit is just for the sake of language. Unit time means that value should be written in the denominator. Similarly, recollect what is acceleration? The change in velocity per unit time. So you write delta V divided by delta T. So per whatever is there, you will write the word after the per in the denominator. Similarly, what are you supposed to do here? Work done per unit test charge. So the work done by whom? The work done by the external force divided by whom are you moving? The test charge is being moved. So if you divide it with test charge, then this particular quantity can be called as electrostatic potential. So I would rather call it as absolute potential, because one of the points is where? At infinity. At infinity, potential is 0. Because the charges are not interacting at all. Whereas when you bring it into the field, what is happening? They start interacting with each other. That is why sometimes this is also referred to as absolute potential. So in physics, whenever you say absolute, right, you are referring it with a known quantity. That is the meaning. Guys, are you able to understand? Right. So this can also be written as, but what is the work done by the external force? It gets stored in the form of electrostatic potential energy and divided with Q naught. Right. Now, what is going to be the SI unit of it? So SI unit is joule per coulomb. The joule per coulomb is what is called as volt. Capital V. The joule per coulomb is what is called as capital V. That is volt. Okay. This is electrostatic potential, which is the name of the chapter. but I need to define another parameter also. What is it? Potential difference. You need to know that. Then what is the difference, guys? When I say potential difference, here also it is written as V only. But I'll tell you what is the subscript you are supposed to write here. Okay. Now, if I take a source charge, then you have a test charge, right? So initially, where will the test charge be? Infinity. So if you are moving it from infinity to the field, you define absolute potential. Whereas you move it between two different points within the electric field, you define potential difference. Are you able to understand? So point A has a potential VA and point B has a potential VB. Then this VA minus VB is what is called as potential difference. So when you want to define potential difference, where should both the points be? Within the field. If you want to define absolute potential, where should one of the points be? At infinity. That is the logic. That's it. In a similar way, can I define electrostatic potential energy difference? First definition, what did we see? Electrostatic potential energy as absolute energy. Yeah. Why? Because one of the points is infinity. Upon on if I want to define potential energy difference, where should both the points be? Inside the field. That is the logic. Okay. That's the simple grammar that is used in physics. Clear? Now, what is going to be the SI unit of potential difference, guys? Same old. Because you're trying, name says no. You're finding the difference between 2 points whose potentials are VA and VB. That's it. Right? VA minus VB is the potential difference between the points A and B. So each point will have a potential. So I'll tell you what is the language they use. So if at all they want to, by the way, did you guys copy this? Yes. See, if at all they want to ask you a question based on electrostatic potential energy, the keyword that they use the question is find the electrostatic potential energy of the system. This is the keyword. Okay, because you cannot define the potential of the system. Okay. Similarly, if the question is based on electrostatic potential, they use the word at a point. Because electrostatic potential is always defined at a point. Electrostatic potential is not defined for a system. Seriya? If they ask you find the potential difference or electrostatic potential difference, then what will they say? They use between the points. Because difference is always calculated between the points. These are the keywords. That's it. If you understand this, half of the chapter is over actually. It's only about how to approach problem. That's a simple thing. Right? So with this knowledge, are we ready to solve some problems in C? Right? Yes. So let me know once you're done. Done? So Bridget, you're done? So everyone, you're copying. Done? Okay. Now we'll get back to textbook. Those who have textbook can keep it open. If not, you can look at the board. Okay. Now read the question carefully before you start solving. Okay. But I forgot one thing. Listen. I gave you that it is U divided by Q naught accepted. But what is this value equal to? It is KQ divided by R. So this electrostatic potential is something similar to whom? So if you want to calculate potential, how many charges do you need? One. If you want to calculate the electrostatic potential energy you need, you don't need negative sum. Here you take only magnitude. Okay. So it is KQ divided by R. I hope I'm clear, right? But this is electrostatic potential due to whom? Due to a point charge. Okay. Now, having all these points in mind, start doing this problem. You first dissect it by yourself and then collect the data and solve it. Don't be in a hurry. Take your time. So calculate the potential at a point. Is that the keyword used? At a point, due to whom? Due to a source charge of value how much? Q is equal to 4 into 10 power minus 7 coulomb. Located 9 centimeter away. Meaning, so I have a source charge and we are interested to calculate what is the potential at a distance of 9 centimeter from this source charge. But if you look at how the system is formed, the test charge was initially at infinity, and from infinity, where did you bring this to? To a distance of 9 centimeter away from the source charge. Is that clear? So you know the formula, applied fast, calculate it. KQ divided by, it is K capital Q divided by R. K is how much? 9 into 10 power 9 into Q is 4 into 10 power 7 divided by 9 centimeter. 9 into 10 power minus 2. Cancel. So 4 into 10 power 16. Oh, minus 7 either. 10 power 2 into 10 power 2. So 4 into 10 power 4. These many volts. 40,000 volts. Right. Now see. From this, obtain the work done in bringing a charge of 2 into 10 power minus 9 coulomb from infinity to point P. So that work that you have done is going to get stored in the form of potential energy. So there are two ways to solve this problem. One is directly define the potential energy. How much is it going to be? K Q into Q naught. So when they ask you work done, right, don't put the minus sign. When they ask you potential energy, put the minus sign. Okay, K Q naught divided by R, right? So K is again 9 into 10 power 9, all those things Q naught, but yeah, into 4 into 10 power minus 7 into how much is the charge? 2 into 10 power 9 minus 9 divided by 9 into 10 power minus 2. So that will actually be 8 into 10 power minus 5 joule. I'll tell you how I got that value. Did you understand what I did here? KQ divided by R is what actually what? Which we calculate in the previous value. That is the potential. So potential multiplied with the charge that you're trying to move will give you the amount of work done. That's it. So next time onwards, right? If at all they have given you the potential of a potential due to a particular charge and another charge is being moved, multiply both to find out the work done. I think this is simple, right?
Sir, can you repeat why should not consider the negative sign?
Because they asked work done. If they asked you potential energy, then you can consider. Then you need to consider the minus.
Okay.
Okay. So for no, it is work done. Where are you saying here? No, it is V only. When I was writing, the screen moved. It is volt. 40,000 volt. Okay, they asked some other question. From infinity to point P, I hope we answered the first part. Read the second part of the question. Does the answer depend on the path along which the charge is brought? You already told one important point. Electrostatic forces, conservative in nature. So conservative forces are path independent. Right? So they have given some other reason, but you can just write the keyword stating that electrostatic forces conservative in nature and is path independent. These are the keywords expected in your exam. That's it. Shall we move on to the next one? Right? So let's try example 2.2. You guys try this. Two charges, 3 into 10 power minus 8 coulomb and minus 2 into 10 power minus 8 coulomb are located 15 centimeter apart. At what point on the line joining the two charges is the electric potential zero? First solve this. Start solving. They told take the potential at infinity to be zero, but we already know. So the null point. See, I have one question, right? Before you start solving, right? Answer this at the question. Had the same question been with respect to electric field. Okay, if you see the system, you have a system of positive and negative charge, except suppose the question was based on electric field, and let's say there is a point P that you're considering. When you're trying to write the expression for electric field due to individual charges, will you take the sign of the charge into consideration? Think about it. I told in the previous chapter itself, if you're writing the expression for electric field at a point due to any number of charges that you have, at that particular point, due to individual charges, will you take the sign of the charge into consideration or not? While you're writing the formula, you don't do it because vector, it's a direct direction will take care, because you know due to positive charge it is away from it, and due to negative charge it is towards it. But in this case, you have the formula, right? Formula, what is the potential due to a point charge? Just now we derived. KQ divided by R is there, right? Since potential is a scalar quantity, you need to ensure that you're taking the sign of the charge into consideration. If you miss it, you will never get the answer. Be able to understand what I'm trying to say. And secondly, whenever there is a question where they're asking you, find the point where the system is going to have zero potential, the question should always be in such a way that there are two unlike charges present, or else you will never get it. If you have a system of two positive charges, you can never have a system where the potential is zero. Whereas, can electric field be zero between two like charges? Think. Listen, my question is very simple, okay? I have two charges separated by distance r. Now I'm trying to club two parameters. What are they? I want you to think an answer. I'm trying to combine electric field and electrostatic potential. Okay. If the question is find if the system has two positive charges, and I'm saying you can keep it. If I say find a point along the line joining both the charges where electric field is zero, will you be able to find for this kind of a system or not? Think and tell me. Don't just randomly tell. Find a point along the line joining both the charges where the electric field is zero. Net electric field is zero. Will you be able to find a point? That is there. That can be there. But these two charges individually will produce electric field. Okay. Where will it get cancelled out? That's what you're almost there. Think about it. It is a midpoint. Does it make sense? This is the answer I was waiting for. So if you have a system of two like charges exactly at the center of the line joining both the charges, the electric field will be zero. But will the electrostatic potential be zero? I just told you I gave you one hint in this problem with respect to this problem. What did I tell you? Electrostatic potential will never be equal to zero when there is a system of like charges. So for potential to become zero at any point on the line joining both the charges, you always need to have a system of unlike charges. Have this in your mind. Why I'm telling this is, suppose there is a question where they've given you two like charges and asking you to calculate the potential. You sit and calculate throughout your life also, you'll never get the answer. You're able to understand. So there is a fundamental problem with the question itself. If at all it is MCQ, they'll give one of the options and none of these. We'll sit and try unnecessary things and waste our time. So if there is a system which does not have unlike charges, potential can never be zero, but electric field can be zero at the midpoint, provided they both are of same magnitude. Is it clear? Are you able to relate both? Because that is how questions will be framed. That is what I'm trying to explain here. Whereas in this question, now think of all the logic and tell me this question has system of positive and negative charges. So is there a possibility of the potential to become zero? Answer is yes. Now comes the next challenge. Where will that potential be zero? Puriyada? So where will that potential be zero? Listen to this. Listen, I'll come. So I'll be solve it together. Listen. So 3 into 10 power minus 8, and this is going to be 2 into 10 power minus 8. I've already put a minus sign there. Okay. Now the distance between them, if I take it to be r. Okay. Let me say there is a point P which is at a distance x from the negative charge. Okay. Then what is going to be the distance of the same point P from the positive charge? R plus x, right? So if I take this as the first charge, this as the second charge, at point P, observe the way I'm writing, at point P, can I say that the potential due to the first charge V1 is how much? K, Q YOLO. How much is Q? 3 into 10 power minus 8 divided by R plus X, accepted. Similarly, what is V2, guys? K minus 2 into 10 power minus 8 divided by R. So X. Since both these quantities are scalar quantities, to find the total potential at a point P, you need to add them algebraically, right? So total potential is equal to Vp is equal to V1 plus V2. If I take that K outside, or K into 10 power minus 8 outside, I have 3 divided by R plus X minus 2 divided by X. This will be equal to 0. Why did I put it as 0? Because I am expecting that point P to have 0 potential. Now, solving this, I get 3 divided by R plus X is equal to 2 divided by X, which implies 3X is equal to 2R plus 2X. So X will be equal to 2R. But what is the value of R? What is the distance of separation between them? 15. So X will be equal to 30. So, but this 30, X is measured from where? From the negative charge. Look at the diagram. Right? So, how will you report the answer? At a distance of 30 centimeter from the negative charge, the total potential is 0. Right? So, that is one point. But when you calculate with respect to potential, right, you will always get 2 points. And both the points will be closer to the smaller magnitude charge. To the charge with smaller magnitude. Why? Because distance, because inversely proportional to distance, right? Due to all the mathematical parameters that are involved, it will always be closer to the one with the lesser magnitude. Okay. So I hope I'm clear, right? We'll calculate and see. One is between and one will be on the other side of the charge of lesser magnitude. Okay. So are you guys clear now? I started outside. Now I'm going to take in between also. That is case 1. Okay. Since I know the answer, I started with that. Okay. Next time, you should think about this point. 3 into 10 power minus 8. 2 into 10 power minus 8. Now, if I take the point P here, okay. Now, I don't know. As of now, I don't know. That is whether it is closer to 2 or whether it is closer to 3. If I take this distance as X, this will be R minus X. I'll give you 2 minutes time. Find out the value of X and tell me. Using the same logic as previous one. No. Will it, you are trying to say it will be 30 centimeters? 6, sir. You got the answer? 6. So 6 means what is R minus 6? 9, right? So you are able to understand that it's far away. Now I'll give you another task. Take the point P on the left of positive charge. So draw 3 diagrams on why you want to clamp it in one. Guys, are you able to understand? Or is it becoming too much of logic? You want me to directly solve the problem? I'll do it. Are you able to think? That is more important for you. Right? So how did you say it is practically not possible? That's, but that we proved only using mathematics. Till that there is no logic existing. We are able to eliminate that minus only because it's a distance. Okay. You're getting minus. Huh? So what is the answer, guys? For the second case, 6. So 6 centimeter from where? 6 centimeter from the negative charge. Means it is at a distance of 9 centimeter from the positive charge. Is it not at a greater distance? Right. Similarly, if you do another task, if you take the point P on the left of positive charge, okay, if you take it, yeah, correct. If you take it on the left of positive charge, if I take this distance as R, okay, then you can calculate this value of x and c, and the value of x comes out to be negative. And the value of x comes out to be negative. Actually, you will get minus 45, correct? Minus 45 centimeter is what you will get, but that value is rejected. Why? Because it is distance. So you cannot say it is at a distance of minus 45 centimeter from the positive charge. It is wrong according to physics. Okay, that is the reason why I told you in the beginning. What did I tell you? It is always, so there will be 2 points. When you are calculating what? When you are calculating the point, the null point where the potential is 0 due to a system, you will always have 2 points along the line joining both the charges. One will be in between the charges, and one will be on the other side of the charge with lesser magnitude. She did it. It's the same logic. If I have to do it in one step, right, you will get something like this: 3 divided by x is equal to 2 divided by r plus x. This is what you will get. Okay, they are in the same ratio. Sorry, they are proportional to each other. Is there anyone having doubt in this? You're clear, right? Nitin, you're clear? So next time, if there is a problem of this sort, even you can solve it. So there is an exercise problem based on it. You can actually do it as a homework before tomorrow's class. I'll show you what it is. The very first problem, I think. First problem. See, 2.1. Take two charges, 5 into 10 power minus 8 coulomb. You can do this as homework. 5 into 10 power minus 8 coulomb and minus 3 into 10 power minus 8 coulomb are located 16 centimeter apart. See, look at the question. It is framed very carefully. At what point in the bracket there is an S? At what point or points? There will be 2 points. On the line joining the two charges is the electrostatic or the electric potential 0. So where will it be close to? It will be closer to the negative charge, minus 3 into 10 power minus 8. It will be on the right of it as well as in between, closer to it. If you want, you can try and see, you will get the same answer. Logic will not fail there. Right? So this is all about the basics of electrostatic potential energy and potential. If this is clear, as I told you, half of the chapter is over. The next part is simple for me to take it. Right? So the next part we will discuss tomorrow. Right? Revise and come. Those who are online, any doubts, please?
No, sir.
Understood, sir.
Okay, good. Revise.
So you said you will upload assignment on first chapter, sir.
Yeah, I'll do that. I forgot. I have the assignment ready, but I forgot to upload. I'll do it today. Okay.
Okay, sir.
Sir, could you upload the study material also?
Study material means that one. Okay, I'll do that.
Okay, sir.
Okay. So if there are no doubts, we can wind up. What